All right, so we're going to start chapter 5, which again looks at a few different kinds of functions. We're going to start with exponentials. Then we'll move on to logarithms. Okay? Logarithms and exponentials are really connected. Okay, so they're good to do them together. We do skip sections 5.2 and 5.3. 5.2 gets into, I think, simple and compound interest, which is more of a banking thing. And 5.3 gets into effective rate, APY, and annuities. It's still very interesting. I do like that kind of stuff. But just it's not really pre-calculus part of our curriculum. So after 5.1, we jump to 5.4. All right, so I just want to start by comparing these two expressions, x squared and 2 to the x. Okay, in each case there, you have a base and an exponent. And the big difference here is one of these is a polynomial, one of them is an exponential. Okay. Anybody tell me which one is the exponential? Is it x squared or 2 to the x? Yeah.
2 to the x.
It's 2 to the x. Okay. And what's the key that tells you something is an exponential? Right, you've got a variable in the exponent, that's part of it. And there are some restrictions on the base. The base can't be just anything. All right, so in the one on the left, that's a polynomial, okay, x squared. Okay, the base is a variable, and the exponent is a number. Okay, in the one on the right, that switches. The base is a number, and the variable is an exponent. Okay, so the first type I just described, that's a polynomial, as long as the exponent is a non-negative integer. And on the one on the right that I described, that's when you get an exponential. Right? But the key is with an exponential, I told you the base can't be any number, and the number that it's not allowed to be is 1. Well, let's take a look and see what would happen if it was 1.
The answer would always be 1.
Right, how come the answer would always be 1?
Because 1 to any power.
Right, 1 to any power would always be 1. That was your exponential function. It doesn't matter how many times you take 1 and multiply it by itself. It's going to stay 1. This would be an exponential function. Take a number just a little bigger than 1. Or you could take a number a little smaller than 1. These are both exponential functions. Does anybody know the difference between the two that I wrote? They are both exponential functions, but there's a big difference between 1.1 to the x and 0.9 to the x. Yeah?
One's going to get bigger and one's going to get smaller.
Yeah, one of these functions is going to increase as you head to the right. The other one is going to decrease. And does anyone know the names we give those when we talk about exponential? Exponential growth and decay. Yeah. So we'll talk a little bit about both of them today. Anybody still need to copy anything here? All right, so looking at the domain of an exponential function. All right, basically, look at like y equals 1.1 to the x and ask yourself, is there any number you're not allowed to raise 1.1 to? No. You can raise it to a positive, you can raise it to a negative, and you can raise it to 0, and fractions and decimals. So there's no restriction on your exponent. But there is a restriction on the base, and I already said it, but I'm writing it again here symbolically. Can anyone translate what that's saying?
It is all real numbers except for 1. All positive real numbers.
Close. Yeah, A can be any positive real number except 1. That's the restriction on the base. Okay, but the domain is negative infinity to infinity. These are all examples of exponential functions. They all have variables for the exponent, and they all have bases that are not equal to 1. You can even have a base that's irrational, like pi to the x. That's fine. Pi is not 1. It's 3.14 and so on. Okay, so now I want to look at some things that are not exponential and see if you can tell me why. And also tell me what they are. They're not exponential. This first one, f of x equals x cubed. Well,
It's a polynomial because the base is an exponent.
yeah, it's a polynomial, okay, because the base
Is a variable.
is a variable, and the exponent is a number. And it's a number that's a non-negative integer. G of x is exactly the same reasoning. Dividing by 2, you could just think of g of x this way. It's 1/2 x to the 4th. That's a polynomial. How about the last one? Is that a polynomial? What do you think? How about Allison? What do you think? Is that a polynomial? All right, so I heard rational thrown out there. It's definitely, well, rational as we defined it was a polynomial over a polynomial. So I guess that would still get back to my first question.
It's a radical.
Is the top a polynomial? No. The bottom is a polynomial, but the top is a radical. So this is kind of like a blend of different functions. We didn't really study one like this, but the point is it's not exponential. Okay, let's graph these two functions and compare them. Okay, y equals 2 to the x and y equals 3 to the x. Does anybody have any thoughts? I mean, I'll give you, they're both exponential, but how they're going to compare to each other?
Is one going to go up like first or something? Not going to go up like more first.
Yeah, one of them is going to increase faster than the other. So what would grow quicker? Taking 3 and raising it to a power, or taking 2 and raising it to a power? 3 to a power, right? 3 to the third, or 3 to the 5th power is bigger than 2 to the 5th power. Okay, much bigger. All right, so let's graph them and just confirm that. Standard window would be fine. My window's a little different, but I think it's okay. So you can see the graph in red is definitely curving up faster. Can anybody tell what point both graphs go through? What coordinate? A little bigger temporarily. 0, 1. Why?
Because anything to the 0 power is 1.
Yes, anything to the 0 power is 1. Doesn't matter what the base is. So that's a point that every exponential function goes through, 0, 1, unless you shift it. If you shift it up, down, left, or right, you could change that point that it would go through. All right, so these graphs weren't too bad to compare. We saw that 3 to the x increases faster, but look at what happens before 0, 1. Okay, set your y max to like 2, and your y min to -2. This is really going to zoom in. Hopefully you can see it. Is the red graph always the one that increases faster? Is that the one that's on top? No, not if you look before the point 0, 1. Okay, in that case, the blue one was on top. So there is that kind of switching of the behavior like we saw with radicals. Okay, they do switch. So the blue one increases faster between 0 or between negative infinity and up to 0. And then it switches. Now, these again weren't bad to compare because they both had the same kind of format. Positive base, positive exponent, positive base, positive exponent. Well, the base is always going to be positive, but you might have a negative with the exponent. And if we get that, we need a way to fix it. So, does anybody know, like, if you had, forget an exponential for now, just look at a numeric expression. How can I fix something like that so that it's positive? Yeah?
Is it 1/2 to the 3rd power? Or 2 to the 1/3? 1 over 2 to the 3rd.
Well, yeah, 1 over 2 to the 3rd, which is the same as 1/2 to the 3rd power. So what ends up happening is that. Okay, it goes to the bottom. Right, so that's the same approach if the base was any number. Okay? To take and make it positive, all you have to do is write it as a fraction and put it in the bottom. Okay? Whatever the exponent is, that stays, these two things have to stay attached. It's just the sign on the exponent changes when you move it to the bottom. So now, let's apply that idea to an exponential. And I want to kind of start by taking one extra step. What number is in front of x in this case? A negative 1. Yep, there's a negative 1. So what I could do, you know what? I'm even going to write one extra step. Think of it like this. It's a to the negative 1 times x. Now, anytime you multiply exponents together, there's a rule. When do you multiply exponents? Or when do you multiply, when do you multiply exponents? When you have a power to a power. That's the only way two numbers would ever get multiplied in an exponent. So now we could write it this way. A power to a power, you would multiply those together and put just what I wrote right there. Now we can do substitution. Okay? A to the negative 1, we already know how to write that. Take that and plug it in right there. So a to the negative 1 becomes 1 over a to the x. So the trick here, when you have an exponential with a negative in the exponent, just take the exponent, make it positive, and take what's inside for the base and flip it. Right, so if I had something like 5 to the negative x, and I wanted to rewrite it, how would it rewrite? Yeah?
1/5 to the x. Oh, with parentheses.
Flip the base and make your exponent positive. Okay, so I'm not going to go through the proof why every time, but those are the steps of why that works. Okay, questions on that? Okay. So let's compare these two graphs. And if you wanted, you could think of this one a little differently. What's another way to write 2 to the negative x? It's the same as 1/2 to the x. Now there's going to be a big difference between these graphs. One of them is going to be growth, and one of them is going to be decay. And I think if you compare the version we rewrote to the original, it should be easy to tell which one is growth and which one is decay. Sometimes it's not so easy if you have a negative with the exponent. So that's why we usually get rid of it. As far as typing it in on the calculator, you can type it in any way you want. Okay, so I'll just type it in original. 2 to the x and 2 to the negative x. This will show it, but you should zoom out a little bit. And make sure you type everything in right. negative should be right there. As far as parentheses, I probably don't need parentheses around the 2, but it shouldn't hurt anything. Okay, what do you notice about these two graphs? Like maybe in terms of like the geometry of them? Yeah?
Well, they both level off, but
Okay, they both level off and they approach a number, but they never cross it or reach it. And we'll talk about that number in a second. Yeah?
One is a reflection of the other over the y-axis.
Yeah, they're reflections of each other. And we're going to show that algebraically in a second, but they are mirror images. All right, now let's look at both of those graphs and analyze the domain and range of each. All right, so just to kind of color code this, the 2 to the x is in blue, and that was f of x. And I did this one in red. All right, so what happens on the blue graph when you look at the domain? How far left and right does the graph in blue go? So it does go in both directions forever. So negative infinity to infinity. In fact, that's the domain of every exponential function. Always. How about the range? Does the graph in blue go up and down forever? No. Does it go down forever? How about just up forever? All right, so it is going to go to infinity. How about the lowest value that that graph reaches? Yeah, it is going to approach 0, but it'll never reach it. And you can check that just by trying some negatives. Negative 2, you're at a quarter. Negative 5.03. Negative 8.0039. So it's approaching 0, and it does approach it pretty quickly. Right, so 0 to infinity, parenthesis, because it never reaches it. Now, how did the domain and range of g of x compare to f of x? They're the same. When you mirror image something over the y-axis, and that's an exponential, it doesn't have any effect on the domain and range. Now, if you mirror image it over the x-axis, that would do something different. Okay, any questions on that? All right. So I want to look at the behavior when the base is basically a positive real number, okay, like a, versus 1 over that number. Okay, so we're basically looking at what happens when the base is a number that's bigger than 1, and all of a sudden when it's less than 1. Okay, so let's think of something like y equals 2 to the x and y equals 1/2 to the x. Basically, just like what we just did. So as x gets bigger and bigger in this type of function, what does y approach? If you let x get bigger and bigger, 2 to the 5th power, 2 to the 20th power, 2 to the 1000th power. Yeah, y approaches infinity. Now, what happens as x gets smaller, but more and more negative, like 2 to the negative 10? 2 to the negative, careful, if you did like 2 to the negative 20, that's not negative infinity. 0, right? 2 to the negative 20 is like 1 divided by 2 to the 20th power. It's a very, very small number, approaching 0. Okay, now let's answer the same two questions for this kind of graph. What happens if you take something where you have a base like a half, and take a half and raise it to a really, really big number, like a half times a half times a half times a half, it approaches 0. And then if you take a fraction and raise it to a negative number, what happens to it? It gets bigger. All right, so the behavior here is the opposite. And it all depends on whether the base is more than 1 or less than 1. Okay, any questions on that? All right. So that's exactly what I just said to you. So the key difference between those two functions is whether you have a base more than 1 or between 0 and 1, but the base will never be a negative. Okay? That's not even exponential. You can't even graph something with a negative base. Well, if you try, let me show you something like this. If you do like -2 raised to the x, and you try to graph it, you don't get anything on the screen. Now, you will get values in the table. What's -2 to the 0 power? 1. All right, so anything to the 0 power is 1. What's -2 to the first power? -2. What's -2 squared? 4. So, yeah, it's all over the place. So basically every other integer is positive, negative, and it's kind of like all over. And then if you start getting into decimals, you can't even graph decimals because, well, it's imaginary when you start getting into decimals. So it's very weird if you try to graph something with a negative base. The simple reason why it's imaginary, try to take -2 and raise it to the 1/2 power. Right? 1/2 means square root. Right? So you're trying to take the square root of -2. So not only do you have things that are alternating between positive and negative, some decimals will be imaginary and some won't. So 1.5 is imaginary, 1.6 is not. That has to do with, think of what's 1.5 as a fraction. It's 3/2. So you're trying to do this, which means this. It means it's the square root of -2 cubed. You can't do that. You can't square root a negative. But other numbers like 1.6, you could probably write that as a fraction. Let me think for 1 second. That would be 16/10, which would reduce to 8/5. And the big difference right there, the denominator is an odd number. You can take an odd root. You can't take an even root of a negative. So negatives here are just crazy. It's a very, very strange graph. A lot of things to think about there. It is kind of interesting. But. All right, so now what I want to do is I want to take and show algebraically that the two functions, if I still have them here, are really mirror images. Okay, I'm going to show that this and that are mirror images. Okay, and the way you show something is a mirror image is take your function and plug in -x into your function. Okay, so don't plug in positive x, plug in negative x and see what happens. All right, so let's go through that. If I plug in -x to change all the x's to negatives, I end up with a to the -x. Any questions on that? Now, does anybody remember how I can rewrite a to the -x without a negative exponent? And if not, just look back in your notes.
Yeah, it's even on the slide before that one.
Yeah, it was right here. Okay, we already went through a to the negative x. It's 1 over a to the x. All right, so I'm going to write that. But what is 1 over a to the x? It's the other function. It's g of x. So by replacing the x with a negative x, we turned it into the other function. Okay, let's do the same thing with this one. Let's replace the x with a negative x. So we get 1 over a to the negative x. Okay. What's 1 over a to the negative x? Right. And if you want to think about y, think about it like this. Flip this part. Make it a to the first power times x. Right? So it turns into a to the x. But what's a to the x? F of x. It's the other function. So the point here is that if you take a function and change the x to a negative x, and it turns into the other one that you're comparing it to, then it's a mirror image over the y-axis. That's how you show something as a mirror image. Okay, any questions on that? We're not going to do too much proving that things are mirror images, but what we are going to look at is how can you prove two functions that are different are actually the same. Okay, and I'll get to that in just after this example, I think. Yeah, it'll be example 3. So transformations on these kind of functions work exactly the same as transformations we've learned on everything else. That's the one nice thing when you study transformations. They're identical on every single function type. So just if you kind of want to see the general list, what it would look like. Let's say you had y equals y base raised to a power with a number in front plus b. That's an exponential that would have all the transformations in it. A is your horizontal shift. B is your horizontal stretch. C is your vertical stretch. D is your vertical shift. And I used the letters that would correspond to the order you do them in. A, B, C, finish with D. Does anyone need me to write down which letter is which on A, B, C, and D? So A is your horizontal shift. B is your horizontal stretch. C is your vertical stretch. And D is your vertical shift. Bless you. Now, B can be negative, and that causes a horizontal reflection. Or C can be negative, and that causes a vertical reflection. We already let B be negative. We've graphed some of those today. I don't think I did one where C was negative. And the problem I'm about to do does have a value for C, but it's not negative. Okay, so let's list out our transformations. How many transformations are happening in g of x? 3. Okay, what is my first transformation? It's going to move shift left 1. Yep. Okay, my next transformation? By how much? Vertical stretch by a factor of 2. And my last transformation, shift down 5. Just like every other transformation class we've studied, the parabolas, the radicals, the rationals, the A and the B always do the opposite of what you would expect. Positive numbers are going to shift left, negatives on A shift right. Bigger numbers for B compress the graph. Smaller numbers for B stretch it. C and D don't do the opposite. Bigger number stretches bigger, smaller number makes it smaller. Vertical. For D, positive numbers shifted up, negatives shifted down. Okay, so you might see a question similar to this on the test where I just ask you, describe the transformations in the correct order. Okay, so any questions on the order of the transformations? So let's look at that problem I mentioned earlier about two things that look different but are actually the same. F of x and g of x are the same thing. I just want to show that they really are. And the hint that I'm going to give you is try to turn f of x into g of x, not the other way around. You could do it the other way around. It's just I think it's easier to start with f of x. Anybody see something I can start off with to just kind of get this thing going, to start to make f of x look more like g of x? There's something really, really different that should be fixed.
Do you use anything with negative 2x?
I do something with the negative 2x and the 3, their placement.
So it's like, wait, is g of x a transformation?
Don't think about it in terms of transformations. Yes, there are transformations happening, but I just want to think about it purely from algebra. So we're just going to use algebra rules to somehow turn this into that.
Well, maybe switch in the exponent where it shows x minus 1.5, the f of x has the coefficient before versus the variable.
So how would you rewrite that?
Negative 1.5 plus x.
So we're going to work with f of x. You could have worked with g of x, but I chose to do f of x. So let's rewrite that one instead.
Okay, so negative 2x
Yep.
plus 3.
Yeah, so that's a good start. At least now we have the term with the x first and then the constant term in the exponent next. Now look at the coefficient of x in the first function and in the second. They don't match. So what could I do to turn my coefficient here into the coefficient that's invisible right there? Something we do a lot when two things have something in common.
Would you have to divide by -2?
Just change one word there, but close.
Multiply?
Instead of divide, what do we do when two things have something in common? Nope, not subtract. It's not a binary operation. It's not like add, subtract, multiply, or divide.
Oh,
Square plus?
square.
Square root.
It's not square or square root. Factor, right? So because factoring preserves what was still there, it's just rewriting it. If I divide by a number, it's going to change the problem. All right? So factor out the -2. And what does that leave me with in parentheses? X. Yeah, it would leave me with x minus 1.5. Okay, now, when we factored it out, we didn't get a decimal, but we didn't get a nice number. But I was expecting a decimal, so that's good. And now I have one thing left to deal with, this 2 to the -2. What can I do with 2 to the -2? Sophie? Right, I can write it as 1 over 2 squared. Okay, Okay, so I rewrote 2 to the negative 2, which is 1 over 2 squared, or 1/4. And as a decimal, 1/4 is 0.25. Okay, so I showed that f of x and g of x are the same. Any questions on that? That's very helpful if you have to compare two functions. Okay, you want them to be in the same kind of format. X first, same coefficient if you can. Try to make them match up.
So what I did was like, when first I put in the right order, and then I put 1 over 2 and made the exponent the opposite sides. And then I took that and divided everything by 2.
Okay, and you ended up with the same same answer? Okay, yeah.
Will that work with the time?
I'd double check it on another one just to make sure that it always works, because I know this will always work. But I'd have to check and see if that would always work.
Okay. Wait, so you just put in the other, like the g of x exponent into f of x, but you forget about the plus 30?
No, I didn't replace anything. What I did is basically I did this. I took x plus 3. Right? Actually, what was the original? Negative 2x plus 3. And I said, I'm going to factor a negative 2 out. Okay, so pretend like you don't even know this exists. Okay? Totally ignore g of x right now. Just look at this. If I take a negative 2 out of the x, or negative 2x, all I'm left with is an x. And here the sign would change. And if I take a negative 2 out of a 3, it doesn't come out evenly. It comes out as a 1.5. So just by factoring out a negative 2, we got lucky. And it turned into exactly the other exponent, which is what I wanted to happen. Okay. If you just made a problem up and you factor out a number, that usually wouldn't happen. But this problem was special to make that happen. Like right here? You just have to kind of think, if you factor out a negative 2 from 3, what would you multiply negative 2 by to get positive 3? And negative 2 times negative 1.5 is positive 3. Yeah. So it's a little harder to factor because, again, it doesn't factor out evenly. It factors out as a decimal. Okay, any other questions on that? All right. So this is kind of a separate little thing. We're just going to graph it and look at it, and then pretty much just move on to the last thing we're going to look at. This is a special graph. Okay, let's just kind of wrap our head around what's happening, and then we'll look at a picture of it. I want to let x get bigger and bigger. Okay, let it approach infinity. What happens to the fraction 1 over x if you let x approach infinity? It gets very, very close to 0. And then what if you add 1? So what's inside here is going to get extremely close to 1. In fact, infinitely close to 1. But then you're going to take a number that's infinitely close to 1 and raise it to a number that's getting huge, an infinitely large power. So let's see what happens. Because we know what happens if you raise 1 to a power. It just stays 1. But what if you raise something infinitely close to 1 to an infinitely large number? Let's kind of see what happens. So we're going to get, in parentheses, 1 plus 1 over x to the x. Okay, what do you notice in that picture? What does it look like there probably is there? Yeah, there is. There's a horizontal asymptote. And there might also be a vertical asymptote somewhere else, but I'm not too worried about that one. Let's check our table and let x get pretty big and watch what number it starts to approach. 2.65. Let's try 200. 2.71. Let's try 5,000. 2.718. Everyone, 2.718, we've all heard of that, right?
Go.
No?
Oh no, it's E.
Yeah, it's E.
Yeah.
I was kind of being sarcastic. I didn't think a lot of people had heard of it, but I'm surprised. Yeah, so you've heard of E.
Yeah.
Oh, good. That's what we're actually going to look at tomorrow. But this is a number that's not as common. Most people don't remember, if they studied it, they just don't remember what E is. But we actually approach the number E, which is 2.718, as x heads towards infinity or negative
Oh, see, I
infinity.
hate Mom. The number E.
Yeah.
That does not make
The number
sense.
Well, it's like the number pi. You use that one, right?
Yeah,
Yeah, but
but
Same
no one
thing.
says the number pi. We just say pi.
Like the number.
Oh, it's a number, right?
No,
Who do pi
it's a
days use?
theory.
It doesn't really
Can
exist.
we bring in pies for pi day?
For Pi Day?
Yeah.
Sure.
My 7th grade teacher.
They have to be
gave us-
store-bought, though. They can't be made at home because of disclaimers from the school.
my mom makes it.
My 7th grade teacher said if we could memorize pi, all the digits in pi for like to the 7, then she would buy us a week full of
I can do
pies.
that
Ah.
right now.
So, E, 2.718, is a horizontal asymptote. And it's going to come up when we study logarithms. So if you're not too familiar with what a logarithm is, you don't really have to know that right now. It's just, this is an exponential function, and it has to do with a number we're going to look at tomorrow. Yeah, but so just kind of a weird idea to wrap your head around, like why is it approaching 2.718, a number that's infinitely close to 1 raised to an infinitely large power. It happens to approach 2.718.
Is that like?
And it doesn't keep repeating.
Is that non-terminating?
Yes, it does not repeat 1828, 1828 forever. The next digit is different. I don't know what it is, but it's not 1. Actually, does the calculator show? No. Sometimes this calculator shows more digits. Let's see. I don't know if I have E on this one.
There's an FE.
Yeah, there's that. That's
What does that mean?
I'm not sure. Maybe it's scientific notation. Like if I typed in 500, does it give me a 2 in there somewhere? Yeah, so it's scientific notation. 5 times 10 to the second. Yeah, I can't really show you more digits because I don't have.
What does the radians and grads part do?
That's trig. So we'll talk a lot about radians when we
Maybe
get to trig.
E's under that. No?
No. I don't think I see it on this calculator, but that's okay. So, just a number I want you to kind of be aware of that's out there, and it's represented by the letter E, just like pi. You know, it's represented by the letter, except it's a Greek letter, pi. All right.
Can you go back?
So the last thing we're going to look at is exponential growth and decay as a word problem. So let's say that we had a population of a town, and at year 0, meaning the beginning of the town when everybody moved there, the population was P. The population of that town is going to increase by a constant rate every year. How would I figure out, let's say, just as an example with a test, let's say you got like a 90 on a test, and I said, I'm going to increase your score by 2%. How do you figure out what your new score would be?
0.02 times. Wait. I don't know.
So your original score is a 90, and I want to increase 90 by 2%.
You do 90 times 0.02 and you add that to 90.
Yeah, you take the original amount plus the amount of increase.
91.8.
Yeah, 91.8. So the pattern I want you to see is you take the original plus the increase. And the increase is the original. It's basically that number that's right there times the increase as a decimal. Okay? So what I could do, let's just take this one. Right? And here I've got the original amount plus the increase. And again, increase is the original amount, that's here, times r. Right? So just like I did before, 90 plus 90 times 0.02. Now, how did I turn what's on the left into what I have on the right? Yeah, all I did was factor out a p, and it's important to write it the way it is in that red box, because if you do, you'll see a pattern. Now, at the beginning of year 2, what is my original population? It's not p anymore. P times what? P times 1 plus r. Okay? That's my new original population. Okay? Starting with p times 1 plus r. And what would be the formula for the increase? P times 1 plus r times r. Okay? You basically take what was right here and multiply it by r, and then add it back to the original. So the box on the left is my original amount. The box on my right, original amount times my growth rate. Add them together, and that'll give me my new formula. Now, what do these both have in common? They both have a p times 1 plus r. So what I'm going to do is factor it out. If I factor it out of the first box, what's left there? A 1. What if I factor it out of the second box? An r. Okay. So here's what I factored out. The p 1 plus r, what was in red. And when you factor out of the first box, you're left with a 1. When you factor it out of the second, you're left with just an r. Now, what does that simplify to? P times 1 plus r times another 1 plus r. Right. So notice for year 2, we had an exponent of 2. Right? If you wanted to figure out how many people would be in this town at year 3, it would be p times 1 plus r cubed. Year 10 would be p 1 plus r to the 10th. So for year t, the formula is p 1 plus r to the t. Okay, that's your exponential growth formula. So p is the original amount that you start with. R is the rate of increase as a decimal. So if it's like 15%, it's got to be 0.15. And t is the time. Now, if we wanted to do decay, we can pretty much use the same formula, except you have to change one thing. Yeah?
Subtract the rate.
You'd subtract the rate. Instead of adding 1 plus the rate, it becomes 1 minus the rate. So if you had, say, a forest that was being cut down at a rate of 2% each year, you could use a formula for exponential decay to figure out how much forest would be left after a certain number of years. Or I could ask the question a different way and say, how many years would it take to only have X amount of acres left? Okay, you can ask the question both ways. Okay, does everyone have the growth and decay formula? All right, so we're going to look at an example where a town has a population of 50,000 people going up at 2.5% a year. First thing I'll do is model it using my exponential growth formula. And then I'll use a graph to figure out how long before the population hits 100,000 people. So we're going to write our population as a function of time. Right, so Kyle, do you think you can tell me the first thing I'm going to start off with and the number that it would be?
So, first thing you would have, would you have the first year or would you have the 0 year?
So we have the information for, we'll call it the year 0. We have the initial starting population.
Okay, so it'd be 50,000.
50,000, yeah. And what would you multiply that by?
1 plus 0, or yeah, 1 plus 0.025.
Yeah, that's 2.5% as a decimal, 0.025. And he said to do 1 plus 0.025, so I'm just going to add those together. 1.025. Okay, and Cody, the last thing I need there, the exponent. Okay, so there's our formula. Now we're going to graph it. And we're going to see when the population hits 100,000 people. All right, so we got 50,000 times 1.025
Yeah, did you get the
to the x. 1 plus the growth rate. So the growth rate is 2.5%, but that's 0.025. So then add 1 to that for growth. If this said the town has a population decreasing at a rate, then I would have done 1 minus 0.025. Okay, and they want to know when the population is 100,000. So how am I going to do that? Yeah, cool. Yeah, graph a line at 100,000. So I don't need to look for any population higher than 100,000, so I'll just go a little bit over 100,000, 110. The minimum population I'm going to have here is how much?
50,000.
Never going to go below that. I don't have to worry about negative years. It's just a question of how many years does it take to reach 100,000. Let's say it does it in less than 35 years. So I'll graph 35 years of data. There's the population. You can see it's not linear. It's curved. So it is going to hit 100,000 people within 35 years. And how do I find where? Just intersect. Okay, so it's going to take about 28.07 years. Okay, assuming that the pattern continues the way it has been. Okay, any questions on how I got 28.07? Okay, we're going to come back to this exact problem with the exact population and growth rate when we study logarithms, and I'll show you how to get the answer with just algebra to get t by itself. Right, so when you're graphing, always be careful about whether or not you should include negatives. A lot of times they don't make sense because of the word problem. And I was going to go through the pattern, how you figure out the growth rate for something doubling. But I think if I just start to explain it, you won't need to go through the pattern. So when something doubles, what percent increase is that?
200%.
All right, let's try it. So what's 200% as a decimal?
No, I said 2.
Well, some people said 200. So I'm going to try that first, just because a lot of people said that in the last class too. It's 2. So let's say you had an original amount that was 20. Now just to be clear, what is doubling? 20 would go to what?
40.
Okay. So that's kind of the end goal. So now if you take 20 and you increase it by 200%, take the original amount plus, and we all agreed that 200% was 2, right? So take original times growth rate. What's 20 times 2?
40.
I got 60. So did increasing by 200% double? No, what did that do? Tripled. So any other thought about
100.
100%? So if we wanted to do a problem with a bacteria doubling, you took your original amount times 1 plus, if something's doubling, what's the growth rate as a decimal? 1 raised to the t. So what does your base turn into? Turns into a 2. And that's basically the formula for bacteria doubling. Which, if you went through the pattern, you'd notice the base is always a 2 raised to the number of times it's doubled, or the length of time to double. It's just like the formula we had, except instead of putting in 1 plus r for the base, we're putting in a fixed base of 2 for doubling. All right, so I've got 100 bacteria, doubles every hour, and I want to know when I'll have 350,000. Okay, so let's write our bacteria as a function of time. So what's the initial amount of bacteria that I had? Started with 100 times, what's my base? 2. That's my 1 plus r, all built into the 2. And t divided by the length of the time to double. This doubles every, how often? Every 1 hour. So in this case, the length of the time to double is just a 1. So you don't need the 1 this time. Okay, but there's your formula. And what I can do is just graph it just like the last one. Type in 100 times 2 raised to the x. Get rid of everything else. And I want to know when it hits how many bacteria? 350,000. To set your Ymax at least to 350,000. Now, technically, I could look at the Ymin as low as 100, but I really don't care what's happening that low. I just care what's happening up at 350,000. And I'm just going to go a little above it. So there's my bacteria. Eventually, it comes up. And I could calculate the intersect and see that after about 11.8 hours, it'll reach 350,000 bacteria, assuming it continues to double every hour.
Can you go back up to the original T the chart?
Yep, you really don't need the chart. That was just if I was going to try to show you the pattern. It's always the base amount times 2 to however many times it's doubled. 2 to the 1, 2 to the 2, 2 to the 3. That's what happens when something doubles. Okay, now the last thing we'll look at is a half-life. So half-life it's kind of the opposite of something doubling. It's the amount of time it takes, usually for like a radioactive substance, for half of it to disappear. So like if you started with, say, 200 tons of radioactive waste, and it had a half-life of an hour. That means after 1 hour, that 200 tons would be down to 100 tons. After another hour, it would be down to 50. After another hour, 25. After another hour, 12 and a half. So it keeps cutting itself in half. So it gets smaller and smaller, but it never reaches what? It never would reach 0. Okay? But eventually it would get small enough it would be insignificant. So what is your rate for a half-life? What's the percentage decrease? 50. Yep. So as a decimal, what would that be? 0.5. So in our original formula for exponential decay, we had p times 1 minus r to the t. Well, if your growth rate is 0.5 and you're decaying 1 minus 0.5, that's where the 0.5 comes in right there. Okay, this one I'm not going to do the graph for. We'll just set up an equation. We'll say for the amount of stuff we have left. Okay, what was the initial amount of substance I had? 5 grams. And my base, 1/2. That's the 1 minus r. It's built into that 1/2. And what's the length of the half-life?
20 days.
20 days. So that's your formula for the situation. Then you could graph it, and you could graph a line at 5 and see where they cross. Generally, like a lot of elements that they create, like in a lab, they have a very short half-life. Some elements have half-lives of like nanoseconds. So basically, the second they create it, it's so experimental that it's gone. So it's very hard to study because it's around for such a short time.
When will Chernobyl be able to go back? What's its half-life?
I don't know. I'd have to look up, but some nuclear particles, the half-life it could be on the order of thousands of years, or even millions. Yeah, some of it is even in the millions of years. So, for all intents and purposes, sometime probably never. But eventually, things drop to safe enough levels, But the question is, when would it be completely gone? Approaching infinity, to be completely gone. All right, so the homework, it's on 268. Okay, just a reminder again, this week, my extra help will be on Wednesday because the test is on Thursday.